Understand the core concept of a buffer. An acid-base buffer consists of a weak acid and its conjugate base. It is highly resistant to pH changes when small amounts of strong acid or base are added. According to the Henderson-Hasselbalch equation, pH equals pKa plus log, conjugate base, over weak acid. Quad A buffer is most effective when the desired pH is close to the weak acid's pK of value, typically within plus or minus 1 pH unit. Calculate the pK for both conjugate acid systems using the table of acid dissociation constants. Ka lactic acid, HC3H5O3. pKa equals log Ka equals log 8.3 times 10 to the power minus 4, approximately 4, log 8.3, approximately 3.1 quad methylammonium ion, CH3NH3 to the power plus pKa equals log Ka equals log 2.3 times 10 to the power minus 11, approximately 11, log 2.3, approximately 10.6 quad. Select the appropriate buffer system. Since the target pH is approximately 3, we must choose the lactic acid/lactate system. pKa approximately 3.1, because its pKa is extremely close to the target pH. This immediately eliminates options A and D, which would form buffers with a pH near 10.6. Determine the stoichiometry required to form a buffer. To make a buffer from a weak acid, we can partially neutralize it with a strong base to generate its conjugate base in solution. A perfect buffer contains equal amounts of the weak acid and its conjugate base, meaning we must neutralize exactly half of the starting weak acid. Analyze the chemical reaction in option B. Initial moles of weak acid, HC3H5O3 in acid equals 100 ml times 1 liters over 1,000 milliliters times 0.1 molar equals 0.010 moles. Quad initial moles of strong base, NaOH in base equals 50 ml times 1 liters over 1,000 milliliters times 0.1 molar equals 0.0050 moles. Quad neutralization reaction. HC3H5O3 plus OH to the power negative gives C3H5O3 to the power negative plus H2O. Because OH to the power negative is the limiting reactant, it reacts completely to convert 0.0050 moles of weak acid into its conjugate base, remaining weak acid, 0.010 moles. 0.0050 moles equals 0.0050 moles produced conjugate base, C3H5O3 to the power negative 0.0050 moles. Calculate the final pH of the mixture because the moles, and thus concentrations, of the weak acid and its conjugate base are exactly equal. pH equals pKa plus log 0.0050 moles over 0.0050 moles equals pKa plus log 1 equals pKa approximately 3.1. This creates an ideal buffer with a pH of approximately 3, confirming option B is correct. The correct answer is option B, a mixture of 100 ml of 0.1 molar HC3H5O3 and 50 ml of 0.1 molar NaOH.